Hello, my name is Maria Santos-Villafranca and I'm going to present the work O-MaMa, Learning Object Mask Matching between Egocentric and Exocentric Views. This work focuses on the task of segmenting a specific object based on its mask from a given viewpoint. For instance, given a third-person view on the left and a first-person view on the right, the objective is to segment the carrot in one view using its mask from the other. It is crucial to ensure that the segmentation corresponds to the same carrot, even when another one similar is nearby. This task is important especially in multi-agent applications, where each one typically has access only to its own sensors or cameras. Consequently, understanding object correspondences between egocentric and exocentric views is essential. While the exocentric view captures both the full environment and the person's body, it contains objects at multiple scales in cluttered environments. Conversely, the egocentric view offers rich details on hand-object interactions, but suffers from motion blur and occlusions. Establishing precise object-level correspondences across views requires fine-grained segmentation and strong cross-view semantic reasoning. For that reason, we propose simplifying it by reformulating it as object mask matching across ego and exo views, leveraging the excellent zero-shot segmentation capabilities of segment anything models. Given the source and destination image, we first generate a set of dense mask proposals in the destination view using FastSum. Then, we compute a descriptor of each mask segment by pulling the corresponding object mask from the DNOV2 feature map of the destination image. Humans leverage visual contextual associations among objects to represent scenes. Inspired by this, we extract a context descriptor by pulling features from an extended bounding box around each mask. Similarly, we extract object and context embeddings of the source mask in the other view. However, it can also introduce ambiguity, since in cluttered scenes, nearby objects often share similar context with distinct object descriptors. Therefore, we introduce a hard negative adjacent meaning strategy that selects neighboring object candidates as hard negatives, encouraging the model to differentiate between nearby objects. In the destination view, we construct a graph of mask segments based on the pixel centers of each mask using the Delaunay triangulation. We also introduce a ego-exo cross-attention mechanism to introduce global representation across views. We compute query vectors from the candidate object descriptors with a linear projection, while the key and value vectors represent the overall source image features. Similarly, we compute the cross-view embedding of the source mask. A final descriptor is obtained from each candidate mask by concatenating its refined cross-view embedding, the context embedding, and the object embedding, and equally for the final descriptor of the source mask. Then, a shallow multi-layer perceptron maps the cross-view embeddings to a latent feature representation. This mapping ensures that both egocentric and exocentric masks are embedded within a shared latent space, enabling a cross-view comparison. Our contrastive loss is based on InfoNCE. We select a batch of elements, one positive and the rest negatives, from the list of closest neighbors around the target object in the other. This mask matching contrastive loss aligns the corresponding cross-view object embeddings while it separates the remaining object candidates in the feature space. We use the novel EgoExo for the dataset for our experiments, specifically the correspondence set. Even our simplest version, the KNN baseline, already surpasses the official XMEM-XECTX baseline from the benchmark. Our full method, O-MaMa, further improves performance, reaching 43.4 total interception over union. Next, we report an ablation of each component of our pipeline. The benefits of training a simple MLP with our novel mask matching contrastive loss, which aligns cross-view embeddings in a common latent space and improves interception over union 23.9% from our KNN baseline. Additionally, incorporating regional context while sampling adjacent negatives during training improves to 31.9%, forcing the model to learn more fine-grained discriminative embeddings in nearby candidates with similar context but different mask descriptor. Next, our ego-exo cross-attention mechanism introduces cross-image content and global information into the object embedding. The joint effect of all our proposed modules especially improves plus 39.6% intersection region over our simplest non-learning version. In this work, we demonstrate that reformulating the cross-view segmentation as an object mask matching problem effectively simplifies the task. Our mask matching contrastive loss effectively align cross-view embeddings, while DNOV2 pulled mask features preserve fine-grained details. The proposed hard negative adjacent meaning strategy enhances the object differentiation, and the ego-exo cross-attention integrates global cross-view context. As a result, our pipeline achieves a state-of-the-art performance on the ego-exo for the correspondences task. Thanks for your attention.